So before I get into any examples of Fourier series, I wanted to do a brief little bit more overview on Fourier series. In this video, we're going to look at something very important, different kinds of functions that we could be given, and like even and odd, and what makes them even, what makes them odd. How does that make our life easier? How does it make our life harder sometimes? And so I'll talk about that. So let's say, for example, we have like an initial condition of this here, right? Let's say x squared. And it's on a period from negative pi to pi. So then our period is 2 pi, length is pi, right? Half of the period. So, can I scroll? It's locked. Okay. So, if we were to graph this, it would look like, let me do this in purple. Let me draw out the intervals first. Let's graph it over 2 periods. So if I'm going to graph this over 2 periods, 1 period would be here. X squared looks like this, right? So I come down, kind of like this. Comes. Oh, it looks awful. Kind of looks like that. It's not exactly symmetric. But then to do it for 1 more period, you just come down. Let me do this. You just come down and then back up, right? Those are the same graphs, by the way. Come down, back up. This is negative pi, negative 2 pi. So now what you want to do is you really just want to isolate one period here. And just want to take a look at that. So when you're looking at this, you want to say, what kind of symmetry does this have? Well, it has even symmetry, right? And you're thinking, well, why does that? So that means f of x is even. Well, why? Well, if we have symmetry, about the y-axis, the function is even. Symmetry about origin, f of x is odd. Let me do a little note. If neither of above is met, f of x, put it down here, f of x has no symmetry. So looking at this function, symmetric over the y-axis. So f of x is even. Now what does this tell us? The fact that we have an even function, so let me do this job here. If function is even, we have a Fourier cosine series if f of x is odd, we have a Fourier sine series. Just think about it, because we know the sine as a function itself is odd, cosine as a function itself is even. So it makes sense. So what does this mean? Well, let me actually separate this out here. If this were the case, we'd be left with the form, if there's an a naught, right, plus n equals 1 to infinity, that term will go to 0, so then we'd be left with, yeah, just a sub n cosine m pi x over L. And the reason why it becomes a Fourier cosine series, here, let's take a look. Y cosine? Y? Well, b sub n goes to 0. Because we know b sub n is 1 over L, negative L to L, f of x sine n pi x over L dx. If our function is even, and if we know that we know we know sine is odd, right? We know that an even function times an odd function is equal to what? An odd function. And whenever you have the integral of an odd function, that's equal to 0. So that's how we know b sub n is equal to 0. So this goes to 0. So then we would be left with something like this. If there's an a sub naught, then there's an a sub naught. There would be in this case, right? Because for this problem up here, we have an even function x squared. So that would, remember, the integral for a naught is just the function. There's no sine or cosine term on that one. So you can integrate that one. But if you had an odd function, you would have no a naught either, right? So that's looking at that one, right? Now just real quick, let's do the odd one quick. So if function is odd, we have a Fourier sine series. Let me just copy this. This one would go to 0 because we know that a sub n is what? Let me look. A sub n 1 over L integral negative L to L f of x cosine. This should be in black because we know a sub n is f of x, this is cosine, n pi x over L dx. Okay, so then in this case we know f of x is, it was even, right? Yeah, even. Oh no, this one's odd. Odd. Cosine is a even function, right? Yep. Remember, odd times an even is equal to an odd. Integral of an odd is 0. So a sub n is equal to 0. So then this term goes to 0 and we're left with this. We only have to solve for b sub n. Now, if f of x is odd, you'll also notice that our a sub naught, just like I just said, right? Because we have what? The integral, oh come on, from negative L to L times 1 over L of f of x d of x. F of x is odd in this case. Integral of an odd equals 0, a sub naught equals 0. So this term would also be 0. So if our f of x is odd, you can see that this is the only term remaining in a Fourier series, which makes our life a lot easier. So you can see that whenever we have an odd case, that's probably the easiest case to solve for a Fourier series. But now if we don't have either symmetry, obviously, if you have no symmetry, like for example, let me add a page here. For example, say we have something like this over a period. Let's just look at one period. You have something like this. Where we have, let's say it's 0 from there to there. And then it is, what would that be, like the absolute value of x from there to there. So that function will look something like this, I guess. Well, yeah, it would look something like it could be something like this. Of course, from negative pi to pi. So in our period 2 pi, length is pi. But you can see for this case, it's not symmetric over the y-axis, and it's not symmetric about the origin. So in this case, we have no symmetry. So we will have a naught, a b naught, sorry, a naught, a sub n, and a b sub n. Right? We will have a value for each term, so we're going to have to integrate for each term. So it's a little bit more of a pain when you don't have any symmetry at all. Now, I just wanted to go ahead and do a brief little reminder of how this works. So whenever you have an odd times an odd, that would be an even. Whenever you have an even times an odd, that would be odd. An even times an even is even. So this will help you simplify your Fourier coefficients, right? Your integrals. Let me do one more quick example. Let me see if I can find one. Let's see what I have here. Okay, that's a good one. Okay, let's do this one. Let's say we have come on. Okay, the function, let's say this 1 minus the absolute value of x, period, negative 1 to 1, so then period's 2, length is 1. So then, I wish this would draw straight. Okay. Let's just draw one period. It will look something like this, right? That should be symmetric, right? But if you take a look at this, symmetric over the y-axis, right? So then let me go back up. Let's take a look. Symmetric about the y-axis, f of x is even, right? Oh, so that was just like this one up here. We should get one that's like the origin. All right. Well, yeah, this one will be even again, right? So we can already tell this is a Fourier cosine series. because it's an even function. And then we can easily be able to tell that our b sub n term is going to go to 0, right? Basically, and then we'll be left with an a sub naught and then solve for a sub naught, a sub n. Okay, let me do another example. Let me see if I can find a odd one. You know what, here's one from, this will be in the next example that I do actually. But let's say we have an odd one here, where it's like, oh yeah, it could just be like negative x, which just goes like this through the origin, right? From a period, we'll do it, you know, negative 1 to 1. So then the period is 2, length is 1. As you can see here, we have symmetric over the origin, right? Now another case could be something like this. That's symmetric over the origin, right? However, you'll notice a problem with this one. Well, however, this would be a very ugly problem to do. Like if you have something like this, we'll do this after. I'm gonna do a bunch of examples, and then we're gonna do what's called half-range expansions. And like say for example, we have something like this, a function that looks like this, and it doesn't, and you don't know if you should extend it, because like you can see that it can't be just continuous, not like a straight line. You can't just put it, you know, over here. Because you can also, oh geez, what happened? You can also do this, right? Well, no, say this is the function right here, right? This is the function that's given. And you're like, well, what would I do with that? Well, you can either do this or this, right? You can either make it even or odd, and either one works technically, but one's a lot better to do than the other one, because you want the function to be smooth and continuous. If you look at these ones up here, smooth and continuous. Well, it's not necessarily smooth, but it is continuous. Continuity is a big important thing about these problems. You can see these are all continuous. However, not necessarily. It's smooth over the, smooth. It needs to be smooth over the period. So you can see how they're all pretty much smooth over the period, except for this one. So we don't have any symmetry anyways. So that one's already annoying. This one here is not smooth over the whole period, but it is continuous. So that is very important. We don't want any jumps in the solution. Now, of course, you can still get a solution if you do it this way. I mean, if you do it this way. But it would be a lot more difficult to get a solution if instead of doing it this way. This would be a lot easier. You'd have a lot less terms in your answer, basically. So that's it for even and odd Fourier series. Now, in the next video, I'm going to basically be kind of skipping all the way to after we solved for our coefficients, and we're going to look at some simplification rules before we actually get into any examples. So I'm just going to look at some higher level simplification. Not sure if every professor teaches it, but I believe they did in my textbook, and my professor did when we did them. There's a lot of simplification methods and rules. Kind of confusing sometimes, but that's why I want to make another little separate video before we do any examples. So I hope you enjoyed this video on even and odd functions. Of course, if you have any more questions on this stuff, you can look ahead at my examples. I have a whole bunch coming out. I think 5 examples I'll be doing. And yeah, that'll go through all full problems, even odd, different, no symmetry. And then we're gonna have another section on half range expansions after that. So I hope you enjoyed the video, and I'll see you in the next one.